Hello everyone and welcome to Engineers Corner. Today's video is going to be the first on a series about statics. Statics is an introductory field of engineering where we study bodies of matter at rest and forces in equilibrium. In other words, we will only be looking at things that do not move, hence the name statics or static. So statics is based largely around Sir Isaac Newton's laws of motion, the most important being his first, which states that an object at rest will remain at rest unless acted upon by some external force. We will see here in our first example that we will be applying forces to a body, but here in statics we don't want anything to move. So we also need to observe Newton's third law, which states that for every action there's an equal and opposite reaction. We will have a set of forces applied to a body that will cause it to move, and it will be our job to find what force needs to be applied to keep that object still. So let's take a look at our first example. We have a point mass centered at the origin of our coordinate system right here. And we have our first force of 200 pounds applied to that body at an angle of 30 degrees from the positive x-axis. Our second force of 100 pounds is applied at an angle of 255 degrees from the positive x-axis, or if we want to say it's an angle of 75 degrees from this negative x-axis by subtracting 180 degrees. And so finally, we have our third force. And we don't know the magnitude or the direction of this force. That's something that we're going to need to find. But we can actually use a little bit of intuition here. We can say that that most of this 200 pounds is going to be going to the right. Not all, of course, because it is applied at an angle of 30 degrees. So some of that is going to be going upwards. But we know a large portion is going to be going right. And then for this 100 pounds, it's a smaller angle. Not much is going to be going to the left. So we can go on ahead and assume that F3 is going to be acting in the left direction. Now, some of this 200 pounds is going to be going upwards. And then the majority of this 100 pounds is going to be going downwards. So we don't really know which way F3 is going to be pointed, whether it's up or down. So for now, we're going to assume it's up, just for simplicity. And so we're actually going to use this concept that I've been using here of breaking down our force into its horizontal and vertical components. And we're going to start with our F1 here. So we have our angle of 30 degrees from the horizontal. We have our 200 pounds acting at that angle. And then, of course, we've made a right triangle here with the x-axis. And so we can, if you remember thinking back to high school trigonometry, we can actually find out this side length here, which we'll call f sub x. We can find it using our trigonometric relations. We can say that the cosine of 30 degrees is equal to this side length fx divided by f1. And so the way we solve for fx is we multiply both sides by f1, and then we're going to plug in this 200 pounds for f1, and we find that our horizontal component is about 173 pounds. So we want to do the same thing for this side length here. We have f sub y, and we could say that sine of 30 degrees is going to be equal to fy divided by f1. And so we'll do the same thing again. We'll multiply both sides by f1. And then when we plug in that 200 pounds for f1, if you remember sine of 30 degrees, that relation is 1/2. We get a vertical component of 100 pounds. And it's important to note here that the fx and fy are not going to sum up to be f1. They're actually going to be greater. If you were to think about this in terms of length, if this was 200 inches, if you had 100 inches here, if this was 100 inches, then you would just have a straight line, right? It must be greater for us to have a triangle. But anyway, we're going to take the same principle and we're going to apply it to all of our forces acting on our body. So we have 200 pounds, right, that we've broken down into 173 pounds to the right, 100 pounds acting upward. And then we're going to do the same thing for F2. If you remember here, this angle from the negative x-axis was 75 degrees. If we consider this a right triangle, or 90 degrees, then this would be 15 right here. But we get a vertical component of 97 pounds acting downward and 26 pounds acting to the left. And so finally, we want to do this for our unknown force. Right, we don't know this angle here, we don't know the force, but we can actually write this out in its components as F3 sine theta and F3 cosine theta. And so here is actually where where the fundamental of statics comes in. If we look at our point mass here, we want to make sure that our forces acting to the left are equal to our forces acting to the right, or I'm sorry, our forces acting to the right are the same as acting to the left. And the same for the vertical direction. We want to make sure our forces acting upward are equal to the ones acting downward. And so we're going to look at each one of these dimensions one at a time to determine what these side lengths or these side legs, what those forces are actually going to be. So if we look back here at our plot, we're going to start with the x direction. I'm going to say that the sum of our forces acting in the x direction, we want to be equal to 0, right? We don't want it to move left or right. So we have F1 here, its x component is acting right, so we're going to denote this as the positive and this the negative. And so F2, remember this component is acting to the left, so we say that's negative, and F3 we guess is also negative. So if we add F3 to this side, we actually have F1 minus F2. We plug in those values and we get that our horizontal component is equal to 199 pounds. Right, and this is a positive value, so we were correct in saying that this is to the left. So we can actually do the same thing for the y direction. We can say the sum of our forces in the vertical direction must equal 0. So F sub y is acting upward, right? So that's going to be positive. F sub 2 is acting downwards. That one's going to be negative. And remember, we didn't really know which way F3 is going to be going, whether it's up or down. So for now, we guess that it's actually positive, right? And so if we solve for F3, we actually get a negative value of 197 pounds. And this simply means that we guessed our direction wrong, right? When we guessed that F3 was acting upwards, in actuality it's acting downwards. This negative doesn't always mean downward. It depends on which way you specify. I could technically say that this way is negative and downwards is positive, and it would be flip-flop, but it just means the opposing direction. So if we were to fix our force triangle here, we would get something like this, right? We have 199 pounds acting to the left and 197 pounds acting downward. And so now that we know our legs, we can actually find our resultant force here. We can't use trigonometry like we were doing before because we don't have an angle here, but we do know both of our side lengths, so we can actually use Pythagorean's theorem. So if we square our legs, the sum of our legs squared is equal to our hypotenuse squared, we can take the square root of both sides and we get that F3 is equal to 280 pounds. So now we know all of the forces acting on our body. We know F3, we know F1, F2, but we still need this direction here. We don't know which way F3 is pointing. We know that it's pointed downwards, but we need an angle. And so this is where we can actually use trigonometry again. We can use our final relation to find this angle here, theta, and we're going to use tangent. So if you remember, tangent of an angle is the opposite side over the adjacent side. We have tangent of theta is equal to 197 divided by 199. And so the way we solve for this angle is we take the inverse tangent, or commonly referred to as the arctangent of this ratio here, and we find that theta is equal to about 45 degrees. And this makes sense, of course, because both of our legs they're approximately equal. So remember, this angle 45 degrees is actually measured from the negative x-axis right here. So we'll actually need to add 180 degrees to get the same reference line for all of our angles. So if we redraw our coordinate system now that we have F3 acting downward, it's going to look something like this. We have F1 of 200 pounds acting at 30 degrees. We have F2 of 100 pounds acting at 255, remember, from the positive x-axis. And finally, we have F3 of 280 pounds. And remember, we added that 180 to the 45, so we have an angle of 225 degrees from the positive x-axis. And now we can say that our point mass, or our body, is in equilibrium in both the x and y direction. So right now we're only looking at 2 dimensions, but you could essentially apply the same thing in 3 dimensions. So we'll continue to explore these topics in future videos. Thank you guys for watching, and please stay tuned for future content.